All right, guys, here it is. The fundamental theorem of calculus. Don't overcomplicate this. It's fairly simple. So we've already learned in the last section that a function defined by an integral is finding the area under the curve from, in this case, a to x of f of t. And what we learned was that really to do this, we can just take the antiderivative. So we can just take f of t, if f is the antiderivative, and then go ahead and find the difference from x to a, substitute it into that function. So what this is saying is that if g of x finds the antiderivative, then g prime just goes back to the regular function that's inside the integral. So it's like if we undo it to find the antiderivative, but then if we take the derivative again, we just get back to where we started. It's a basic idea. And that's exactly what part 2 is basically saying too. So we're going to talk about these two parts, see exactly how they work, but I want you to notice that in this case, if you look at this, this said f of t. And if you notice, now it says f of x. So we just replace from a to x, we just replace that t with the x. And then same thing down here. We already talked about kind of the way that that works up here. So let me actually get into some examples and show you. But first we're going to take a look at a graph. All right, so we have g of x is given to us, and this is the function for g of x. So it says to evaluate for x equals 0, 1, 2, 3, 4, and 5. So in other words, we are going to go from a equals 0 to each of these different values. So a equals 0 to 0, and then to 1, and then to 2, and to 3, and to 4, and so on. So for this function, for part A, g of 0. Basically that's saying find the area from 0 to 0. Well, the area from 0 to 0 is just 0 because there's no width. But then when we go to g of 1, the question is what's the area on this graph from 0 to 1? Well, I see that it is a triangle that has a base of 1 and a height of 2. So I know that area would be 1. And then we go to g of 2. Well, g of 2 adds that triangle of 1 plus these 2 additional squares. So a total of 3. Then g of 3 looks like we go ahead and add on about, not quite, or a little more maybe than a half. So I'm going to go with that this area in here is about 1 1/3. Or sorry, it's a little more than 1, a little more than what g of 1 was. So I'm going to go with it's a little more than 1 1/3. So I'm just going to say that if I add that to the 3, I'd have 4 1/3. So in other words, the area all the way over here under this curve is 4 1/3 approximately. All right, well, if I'm going to call, go ahead and just erase all that. If I'm going to call the area from 2 to 3 positive 1 1/3, this area right here looks identical to it, but it's negative, so I'm going to call that negative 1 1/3. So that means the area from 0 to 4, because this area would cancel out with this area. One's positive, one's negative, they're the same value. So g of 4 just gets us back down to 3. And now, again, this looks about the same as the negative 1 1/3. So I'm going to go ahead and take off 1 1/3. I'm going to say that g of 5 is about 1 2/3 if I take off 1 1/3. All right, so those would be the area under the curve. And so we're going to go ahead and we're going to be able to sketch a graph of g, or the antiderivative based off of this. But we need to talk about where do we have a maximum, where do we have a minimum value. Now remember that we're looking at this as though it's the derivative. So we know that we have a maximum when we switch from a positive graph to a negative graph, so that it's increasing to decreasing. And I notice that on this graph, I see right here at I am above to begin with. I'm always above the x-axis until I hit 3, and then I go below. So it looks like I would have since I'm going from increasing to decreasing, I would have a max at g of 3. So at g of 3, I would have a maximum value. And since our lowest value is g of 0, I'm going to say that g of 0 would be our absolute min for this. All right, now we're supposed to go ahead and sketch what the antiderivative would look like. What does the graph of g look like? All right, so g of 0 is 0. G of 1 is 1. G of 2 is 3. G of 4 is 4 1/3. Then we come back to 3. And then we end at 1 2/3. So if I go ahead and sketch that, connect it, it looks something like that. And so again, we're just relating the derivative and antiderivative again. That's the whole point of all of this. So the integral graph is going to be our antiderivative, or sorry, our derivative graph. So in order to find the actual function, we find the antiderivative graph. All right, I'm going to show you both parts of the fundamental theorem of calculus. So part 1 on this one. If you refer back to part 1 in your notes, part 1 basically just said that we can do g prime of x by just taking our derivative, or sorry, our function here. We know the derivative of g. If g's value would be the antiderivative of this integral, then g prime would be the derivative of the integral, or the derivative of that answer, which just gets us back to t squared. But we don't want it in terms of t. As you see up here, we have an x. So the first part of the fundamental theorem of calculus tells us that as long as this is a constant right here, and this just goes to x, you can go ahead and just plug the x in. So you can just do direct substitution, and that would be the derivative of g. So now the second part is actually kind of more of a proof. So the second part actually tells us to evaluate the integral. So if I evaluate that integral, I know that it would be t cubed over 3, and we're going from 1 to x. So I'm just finding g of x right now, not g prime. And then I know that I go ahead and plug in x and subtract, plugging in 1. All right, so that's g of x. Now, if I'm going to go ahead and do g prime of x, I'm going to take the derivative of this guy. Well, I know the derivative of x cubed over 3 is 3x squared over 3. The derivative of any constant, which 1/3 is just a constant, is 0. So this is going to equal x squared. So if you notice, we got x squared here, we got x squared here. Either way gets it for us. But this way kind of is a way to prove it. The first part is just allowing us to do it. Now, we do have some catches with this. You're probably thinking, well, that seems pretty easy. But we're going to do one more example before we get to that catch. So let's go ahead and do this one here. And we'll go ahead and look at the first part. The first part tells us that we can go ahead and find g prime by simply just plugging in x, so doing direct substitution. So g prime would just be 1 plus x squared. Now if we do the second part, again, it's kind of more like proving. So we'd actually evaluate the integral. So it would be t plus t cubed over 3, evaluated from 0 to x. And so if I go ahead and evaluate that integral, I would have x plus x cubed over 3 for the first part, minus 0 plus 0 cubed over 3 for the second part. And of course, this just goes to 0. So g of x is equal to x plus x cubed over 3. But I want g prime of x. So I'm going to go ahead and do the derivative of that, and I'm going to get 1 plus 3x squared over 3, or 1 plus x squared. And if you notice, that's the same thing here, only with an x in it. It's the same thing there. So we get the same thing every time. And if you guys go ahead and pause the tape at this point and give this one a try, just try it. It's just as simple as the last ones, but I'm only asking you to use the first part. Now, if you want to go ahead and do the second part, you can. Actually, I take that back. I haven't taught you how to do this one with the second part. We'll learn that one tomorrow. So you can only do the first part of the fundamental theorem of calculus on this one. So go ahead and pause the tape. Give it a try. All right. Now that you've done that, again, if we want to find g prime using the first part of the fundamental theorem of calculus, we can simply just plug this into any of the t's. So in other words, it's just 1 plus x squared. And that's it. It's done. I want you to take a look at this one here for a second and notice what is different. What has not been the same that we've done on the other ones. I hope that you notice that it's this x to the fourth here. We haven't seen that yet. And that's the catch. So this still works similarly. We can still, and also just a reminder really quick, this d dx means to find the derivative. That's what it's asking us to do. So if we're going to find the derivative of this integral, we can still use the direct substitution that we used before for the fundamental theorem of calculus part 1. The catch is the inside function is not just x. So using the chain rule, we know that we have to multiply by the inside function's derivative. And the inside function's derivative would be 4x cubed. So the final answer for this guy would be 4x cubed secant x to the fourth. All right, and for our last example, again, I'm going to ask you to take a look at this and see what you notice is different. All right, we do only have an x in this one, but the difference is the x is where the a is and the constant is where the b is. So we need to rewrite this integral so that the x moves up here instead. We learned that we can switch the a and the b by simply negating the integral. So our first step is to rewrite this integral, negating it, making it a negative, and flipping the a and the b so we can apply the fundamental theorem of calculus. So then now that we have that, we can go ahead and do our direct substitution. So we just get negative sine x. That would be our f prime. All right, come see me if you need help. Sorry I wasn't there today.